Okay, we are now on air. Hey, everybody. How's it going? This is Asib Qureshi, and I'm going to be giving a presentation on scalability and memory as they apply to computer science algorithms. And this is going to be primarily around JavaScript, because I know this is a big JavaScript meetup you guys have in New York City. So you should be able to see, and I just want to confirm from people who are in the chat who are beaming in, who are not actually there in person in New York City, that you can see me, that you can see the live audience, and that everything's all good. Can we get some all goods? Awesome. Great. Okay. So we're going to go ahead and get started. And I'm going to throw up a screen share. It's going to get kind of crazy for a moment because I think it's going to like show you, it's going to show the screen and the screen is going to show the screen. So you're going to get this infinite screen thing. But I have to do that in order to show the presentation. So 1 second. Okay. I'm going to pop this thing up. So this is going to get gnarly, but here we go. Okay. So today our talk is going to be about scalability and memory. So, for a lot of people here, you guys might be front-end developers, you might be new programmers who are just getting into, understanding computer science. You might have gone through a boot camp, you might be self-taught, you might be even a professional developer. This is kind of basically anybody who's in the area where they know some stuff about programming, they understand the basics, they can write a program and parse a program, but they don't know that much about computer science and they want to learn. And kind of get deeper into understanding how all of this stuff fits together. So this is going to be all in JavaScript. I'm going to be using ES6 syntax. If you're not familiar with ES6 syntax, probably the only real big thing is the fat arrow. It's basically like a lambda, or like a anonymous function that's defined in sort of inline. If you're not familiar with that, don't worry, it's not a big deal. I'll explain it the first time that we see one. So if you're going to be coding alongside and doing the exercises, then go ahead and jump into this link, bit.ly/1tpjce6. At this link, so it goes to a GitHub repo that I've set up. Right now, we won't be doing any exercises quite yet. This is just the very beginning. Yeah, that'd be great. Can somebody post a link in the chat? It might be hard to see. Actually, a quick question for those who are in the chat. How blurry is this? Is this can everyone actually read the text here? Cool. Excellent. All right. So let's go ahead and get started. So the first question is, how do you measure an algorithm? So if I have an algorithm that I'm writing to try to solve some problem, how do I know how good it is or how fast it is? We want some way to be able to talk about this because it seems like an important concept, right? And whenever we're talking about algorithms, we're usually not thinking about very small scale algorithms, like maybe something you might write on like a script to scrape a web page or just solve some really kind of teensy-weensy problem. Usually when we're thinking about algorithms, we're thinking about something that's like on a big scale, where sort of the stakes matter. There's a lot of money involved. There's a big company involved, like Facebook or Google or whatever, right? We imagine these large numbers, and we want to have some structured way to think about how good is an algorithm when we're thinking about that kind of scale. So, if I ask you this question, how would you tell me how good your algorithm is? Your first instinct. So actually, let's look at this function right here. And so I guess this is the first time we'll be looking at this. Where's my mouse? Oh, here's my. Oh, that's really weird. I can't actually see my mouse except on the other screen that I'm casting this on. Hold on 1 second. Why is that arrow there? Okay, whatever. We'll ignore it at the moment. So there's this reverse function, right? And by looking at it, hopefully you can understand what it's doing. There's this array of reverse characters. It splits the string, and then there's this for each character in the split string, you unshift it on the beginning of an array, and you just join that array together, and then you have a reverse string. So the question is, how good is this algorithm? How can we describe the speed or the efficiency or whatever term we want to use? How do we talk about this algorithm? So one thing you might think is we could measure the clock time, okay? And the way you might think about clock time is literally just, count up the amount of seconds it takes or the amount of milliseconds or nanoseconds it takes for this thing to run, right? So we might say, well, clock time, right? Does that work? Can we try measuring clock time? The problem is that clock time depends on who's counting. Okay, what do I mean by that? What I mean is, let's even say, so taking aside the fact that it might work very differently on different size inputs, let's say that it scales totally continuously, And, everybody's going to measure how long this thing takes for input, 10,000, like 10,000 letter string. Well, the problem is that, it might run faster on my computer than it runs on your computer, than it runs on, a GPU, then it runs on a supercomputer, then it runs on, a totally different set of hardware with a totally different, load. The other problem is that actually, even on one machine, even if you standardize the hardware on which this algorithm we're going to run, you would still get different numbers, because sometimes, the garbage collection is just going to be a little bit different, and you're going to get slightly different numbers on the same machine. Or sometimes, there are other processes running on your computer. So even with the exact same hardware, you're going to get different times. I mean, the variation won't be huge if you're using the same piece of hardware, but it still won't be one fixed number. So clock time doesn't really work that well for describing the effectiveness of this algorithm. And the other thing, of course, is that what clock time are we going to actually measure, right? Are we going to say this algorithm takes 10,000 seconds, but for what input size? What input size are we going to measure it for? And how do we know that that's the right number for which to slap down a time count for this algorithm? It doesn't really work that well for a number of reasons. So clock time is out. Clock time doesn't really work to measure an algorithm. Now we might think, okay, well, if you look at an algorithm, you can just count the number of lines or like the number of instructions or something like that. And maybe that's a good measure of how effective or efficient or how long this algorithm takes. Now this one is also no good. So here's a function that you might look at and it seems really stupid. That's because it is very stupid. What this does is it literally just it starts, okay, here we go. It does this for loop, and it just counts up from 0 to x raised to the y power, and just does nothing. It just counts up and does nothing, and then it just adds the two numbers. So this is like a really bad adding function. It just does a bunch of crap for no reason. And this is 2 lines, but it's extremely slow. So the fact that it's 2 lines doesn't mean anything. So we can that is clearly out. Okay, what about the number of CPU cycles? All right, so ignore clock time, because clock time depends on the processor, depends on whatever stuff is going on. We can ignore the number of lines because that can be just about anything. So what if we count the number of CPU cycles? So that's got to be constant, right? Even if the CPU cycles are running by really fast or whatever, but this is just like the number of zeros and ones that get processed by the machine at some point, right? So if we count CPU cycles, then the hardware, doesn't really matter, right? Like it's just this algorithm takes this many computer cycles for this size. So that's not an unreasonable place to go. We can ask that question. And problem is that if you're looking at a language like JavaScript, there are many, many different implementations of JavaScript. Okay, so just looking at this list right here, you can see there's Rhino, which is written in Java. There's V8, which is written in C++. There is I can't not really know most of these. Duct tape, apparently, which is written in C, right? So basically what that means is that, you think you're writing JavaScript, but in fact, the actual machine code that's running, the CPU code that's running, depending on what JavaScript runtime you're in, will actually be executing Java code, which will be different from when you're executing the C++ code, which will be different when you're executing the C code that the JavaScript is actually interpreted in. So you can write the exact same algorithm, and it'll get compiled to completely different instructions on these different runtimes. So there is no single number for an algorithm that's like, for like a JavaScript algorithm that is the number of CPU instructions that this turns into. Same thing with like even compiled languages. With a different compiler, you will get different actual machine code and a different number of CPU cycles for an algorithm. So it doesn't work because it depends on the runtime. And because there's so many runtimes, we can't just ascribe one number to an algorithm. And so we kind of run into this again and again. We can't just get one clean number to attach it to an algorithm. And they also don't really capture what we care about. Okay, because even if I told you, okay, for size 10,000, this thing takes X amount of time, that it doesn't really contextualize that much about the algorithm. It doesn't really tell you that much that's useful. And it's too flaky. It's too dependent on hardware. It's too dependent on way, way, way too many things. So the solution to that is big O. And this is kind of the way that we're going to describe algorithms in a way that's not dependent on not dependent on hardware, and is more general and easier to kind of contextualize. So big O is coming in to save the day. So big O is also known as asymptotic analysis. So asymptotic analysis, if you don't remember from maybe high school geometry what an asymptote is, an asymptote is basically something that it's sort of like you can imagine it as a line that a function approaches but never quite reaches. So when we talk about asymptotic analysis, really what we mean is like when n when the input size goes to infinity, what is the shape of the way that the algorithm grows? So when the numbers get huge, when the input size or like the number of elements in an array or the size of a string, if you're reversing a string, when that gets really big, how does the algorithm scale? Okay, so this is not necessarily a reflection of the literal amount of time that it takes. It's more the rate of growth or sort of the rate of change as the input gets bigger and bigger. That's fundamentally what big O captures. And another way of putting this is how fast do the numbers get just unmanageably big, right? How fast does this thing just balloon out of control, and we can't really manage the growth of this algorithm anymore? So that's kind of the idea. Another way to think about this is, a good shortcut for thinking about big O or thinking about like the asymptotic runtime of an algorithm is just imagine that your input size to your algorithm is 10 million or 10 billion or just some ridiculously large number. Will your program be able to resolve? Like, is it just going to take more CPU cycles than exist in North America to actually solve your algorithm or actually compute your answer within a day? Or is like this something that's pretty tractable if the input size is really, really big, right? Again, this is about scalability, not necessarily speed. And scalability is a really important concept. It means, even if this thing takes a lot of computing resources, how does it behave when the input size doubles or when the input size 10x's, right? If when your input size 10x's, the amount of time that you're going to have to take 100x's or 1000x's or 10,000 times x's, then that's not a scalable algorithm. Even if it's not super fast, it's not scalable because when you get bigger and bigger inputs, this thing is not going to be able to handle those larger inputs. That's really what asymptotic analysis is fundamentally about. So let's talk about big O. So big O is a kind of mathematical notation. And what that means is it's used primarily in mathematics, but it's also used in computer science. It's used slightly differently in the two contexts. So computer scientists tend to be a bit more loose with the way they use big O. Technically, in mathematics, big O connotes something quite different than it does in computer science. But computer scientists, I guess, are just kind of lazy. And so they just use big O to mean the asymptotic rate of growth. And generally, it means like a tight bound also on the asymptotic rate of growth. That's usually what we use big O to notate. So the way to understand this is that if I say this is, ON, or big O of n, that means that is the way that this thing scales relative to the input size when the numbers get big. Meaning the amount of time this algorithm takes scales proportional to n, or to n squared, or to the log of n, or something else. So here's what big O notation tends to look like. It's just a big O. That's why it's called big O. And then in parentheses, usually you will have some function, and that function is stripped down. It's simplified. There are no constants. There are no other factors other than the largest dominant factor. There are no coefficients. It's just ON. So this is basically the way you'll see big O notation. And just to be really clear, what these three notations mean is ON means this scales proportional to the size of n, where n is the size of the input. That is how long this algorithm will take. If you have an input that is 1,000 things, this will take about 1,000 somethings long. N log n means that this grows proportionally to n times the log of n. And O of n squared means that this thing grows proportionally to the input size squared. So how long this algorithm takes is usually going to be proportional in some way to the input size squared, which means that it grows in time really, really fast with the input size. Okay, so n here refers to the input size, and it's important to understand what n means, because we're going to use n all the time when we use big O. So what do we mean by n? Like, it seems like potentially kind of vague. So n just means the input size, and the input size, how you measure that, just depends on the algorithm, right? So if the algorithm takes an input, so for example, if it's like reverse a string, then the only real way to measure the input would be the size of the string, right? Or if the input, if the function is to sort an array, then the only real, sensible way to measure the size of that input would be the number of elements in the array. It can also be the number of bits in a number. So for example, if you are, writing an adding function or a square root function, usually the way that we'd measure the input size there would be the number of bits that comprise the number that is the input to that function. But it doesn't really matter. You can represent the n however you want. But you have to know what is the input size that I'm referring to as n. What is the actual quantity that scales up and down as my inputs get larger or smaller? Cool. So ON means the algorithm scales linearly with the input, okay? And by linearly, I mean it scales like a line. So you might remember, again, from geometry. We're not going to be going into much geometry, but just, just a very brief reminder of how it all works. If you plot the line y equals x, that is just a line that goes through the origin. It looks exactly like that. And that's basically what it means. Whoops. Hold on. Okay. Oh. Yeah. So this line is the line y equals x, or you can think of it as y equals n, where y would be the amount of time that this thing takes. So the idea is that if I have one more element, I will take one more unit of time. If I have 10 more elements, I will take 10 more units of time. And if I 2x my input size, I will 2x the amount of time I'll have to take. So that means the algorithm scales linearly because it scales like a line. Cool. So by the way, if you have any questions or you're confused about something and want me to go over it again, feel free to post something in the chat. I am looking at it as I'm delivering the presentation. So if I've glossed over something or something doesn't make sense, feel free to ask a question and I'll stop and try to explain. So now another thing to be clear about when we talk about Big O, and I kind of alluded to this a little bit, is that when I say it scales linearly, so, I said it scales like a line, the line I showed before just goes, 1, 1, 2, 2, 3, 3, 4, 4, all the way to infinity. Scaling linearly can mean that it's sort of like one-to-one, right? If I add one more, yes, I'm sorry, the PowerPoint is not available yet. I'll post the PowerPoint afterwards. You'll have to just view it from the actual presentation at the moment. Sorry about that. Yes, so when something is scaling linearly, that doesn't necessarily mean that there's one iteration per extra input. It can simply mean that there is a constant number of extra iterations per input. So if I add one more element, there might be 3 extra iterations or 3 extra operations that I have to do, or 5 extra operations, or even 100 extra operations. But the point is that it's a constant amount. If I always only have to do 1 more thing, or 5 more things, or 100 more things when I add another element, that is scaling linearly, because that sort of ratio, that instead of being 1-to-1, it might be 20-to-1. But as long as k is constant, then it's still a line. It's just a line with like a steeper slope, if that makes sense. But it behaves linearly. So that would still be called a linear algorithm. Even if I have like 5 things that I do per extra element, this algorithm must scale linearly. And only when you start getting higher polynomials does it not scale linearly anymore. So Brian asks, how much importance is scalability versus memory usage? How much weight is each given in common analysis when designing for big companies? Let me bracket that question because it's kind of it incorporates a lot of different things in this presentation. I'll answer that toward the end. So ask that again. At the very end of the presentation, there'll be a Q&A. And if you have any like sort of large scoped questions that are not about like the specific slide or like the specific thing I'm talking about, please save it for the end because that's going to be the easiest way to like kind of address everything and not have to jump around. You know what I'm talking about. Cool. So let's move on. So in Big O notation, we strip out any coefficients and any smaller factors. So the fastest growing factor wins. The fastest growing factor is also called the dominant factor because it sort of dominates all the other factors in a coefficient, in a polynomial or a non-polynomial. So the easiest way to think about this is just, when the numbers get huge, what part of this expression is going to dwarf everything else and how big it is, right? So I'm going to show you a couple examples here. So in Big O, we strip out any coefficients. So here we've got a coefficient of 5. So this means like, it's sort of 5 iterations or 5 somethings for each input. We would reduce that to just say ON. We always strip out any coefficients because they sort of don't matter, right? Because again, we already talked before about like how this counting problem, right? Like counting just kind of sucks. So we ignore all the problems of counting because it might run differently on different hardware, might run differently on different compilers or optimizers or whatever, but it's never going to have a different, high order factor. Basically, it's never going to be not ON, but it might be like 4N or 3N or 1N based on like really smart things your compiler does, or it might be like 7N if you have a really crappy JavaScript runtime that you're using. So we ignore all the coefficients and we just reduce it to ON. Now here, this is a nice example that shows you, there's this other smaller factor. So the coefficient, of course, gets dropped away. We don't care about the 1/2. But there's also this constant factor, like 1/2 n minus 10. We strip out the constant factor. We strip out 8 because it's a smaller rate of growth than n. So like when n gets huge, you can imagine when n becomes like 10 million, that minus 10 is not going to make a difference. It's just going to be a blip in what's actually happening in this function. So we'll just say this grows on the order of ON. So another few notes to just know how big O notation works. And we're going to do an exercise pretty shortly on big O notation so you guys can get a feel for how it works. So anytime that you have a constant, so some O of k, so O might be like 500 or 200 or 30, we would say that reduces to O1. Okay, and the reason why we say that is because it doesn't grow, right? So 1 is sort of the simplest number that doesn't grow. That's non-zero. So we just say anything that's like a constant, even if it's a really big number, it's O1 because it doesn't grow with the size of the input. So whenever there are multiple factors of growth, so I showed you we strip out a constant factor, but even when there are non-constant factors, so factors that depend on the size of the input, the most dominant one wins, and that becomes the only thing you include in the big O notation. So here we've got many factors, right? We've got this, this quartic factor, n to the fourth. Then we've got this quadratic factor, n squared. Then we've got this 40n, this linear factor, right? But if you think about it, when the input size gets huge, when the input size becomes 10 million, the n squared and the 40n are not going to make a difference. They're not even going to make a blip in how big this function, how long this function is going to take. So we just strip away everything else and we just reduce this to on to the fourth. So now another thing that might happen is you might have an algorithm that takes two inputs, right? So one example of this might be like if you have an algorithm that has a matrix, the matrix might have a length and a width, and those are two different inputs, right? So based on the length and based on the width, this algorithm might take different amounts of time. Another common algorithm that might have two inputs is like, let's say you want to find all of the common substrings between two strings, right? Well, then you clearly have two strings as your input, and you need to be able to talk about the two inputs in some way. And it might take longer in one input than it takes in the other. So when you do that, you usually use two factors to describe the big O of this algorithm, right? Because it depends on two different inputs. And if one of the inputs is really big, one of the inputs is really small, you should know that. You should be able to reason about how long this algorithm is going to take and how well it's going to scale, and also maybe how you should order your inputs based on how the function runs. So, for example, if you have this O n times m thing, basically you have these two factors. You represent it as O n times m. It doesn't matter if one variable probably dwarfs the other, okay? Unless it's like for certain that one variable is bigger or more dominant than the other, you always include both factors in your big O notation. So anytime that you have two inputs and you don't know for sure that one is smaller, include both. So just kind of a note on how this stuff is usually measured or sort of talked about. If you have two inputs that are added together, this is considered to be a linear time algorithm. And we're going to talk a little bit about like sort of the names for these things. You can say ON. If you have two inputs, you would not say ON. You would just say linear to describe the rate at which it grows, or you could say ON plus M. So here's a more complex one, right? Where you have these two inputs, where this is like 2 to the n plus log of m. So if you don't remember what a logarithm is, it's sort of the inverse of exponentiation. Basically, logs are really super small, and we'll look at logarithms in a little bit. But so 2 to the n seems like it's really, really big, right? So it might be like, well, if we have 2 to the n in one of our factors and log in the other one, then maybe we just should say 2 to the n because like the log m is not really going to matter. Even in this case, you cannot do that. You should always represent both inputs, even if one input is clearly going to be way more expensive than the other. You'd still include both factors because you sort of, you never know, right? Because if n is really, really small, but m might be really, really big, it could be the case that the m ends up becoming a more dominant factor than the n. But you would say that this algorithm here is exponential because it's exponential in at least one of the inputs. And just a note, actually, that it's probably worth just as a little footnote. This right here, n times m, we would call this quadratic because it sort of grows like a parabola in the two inputs. So if you multiply the two inputs together, you'd say it's quadratic. If it's like n squared times m, you might say it's cubic, something like that. But it's not really huge deal. You can just say n times m or whatever. Cool. So what I want you to do now is, if you have a some kind of worksheet open, or just open up a file in your text editor, and I just want you to write for yourself what you think the big O notation of each of these functions is going to be. So this is sort of a way to kind of test yourself and see if you understand the sort of the norms of big O notation. Okay, so the first one is O3n plus 5. So go ahead and write down in your own text editor what you think the big O notation here should be. And I'm going to go ahead and just write in the chat. If you want to read in the chat, I'm going to go ahead and write the answers. So if you want to take a little bit more time, you can go ahead and do so without looking at the chat. Cool. Here's the second one. And so decide what you think the big O notation for this should be. Okay, here's the third one right here. All right, this one a little bit more involved, maybe. And here's the last one. There's no real algorithm that I know of that actually has a runtime like this, but I just thought it'd be kind of cool. Okay, so just going to real quick go over the answers to these. First one is on, strip out the coefficient and the constant factor of 5. That doesn't matter. Second one, n squared obviously dominates the n, so the n just drops away. Coefficient 1/5 n squared drops away, just becomes n squared. Third one, log n. Just a note in case you totally forgot what a log is. Again, it's the inverse of exponentiation. So the log base 2 of 8 would be 3, because that's the power you have to raise 2 to get the input, which was 8. So logarithms grow very, very slowly, but they still scale with the input. So if the input potentially gets big enough, it'd be very hard for log n to ever be more than 5,000. So it's kind of like not really in the feasible universe that the log n could dominate 5,000. But we would still say that this is O log n because the 5,000 is technically constant. The third one, it's very simple, just the m cubed. The 50 is a constant, so that goes away. And then the n is linear. So you just be m cubed plus n. And the last one is basically the only thing you do is you strip away the constant factor, the coefficient from the m squared. And it's just n log m plus m squared plus n times m. And the reason, so you might think like, well, this n times m though, that's quadratic, right? We already have this quadratic factor. But because these are all specific, like because if n is really, really big, that might change the way we think about this algorithm. Or if m is really, really big, that might change the way that we approach this algorithm. And so if one is small, one is big, one is big, one is small, there's actually, we want to preserve all of this information when we're thinking about the way this algorithm scales. So you would not throw away any of the factors, even though this is sort of quadratic twice. So this is not something that's going to come up with any frequency of like, oh no, I got to make sure that I do that. You're never going to get something like this on the interview because it's kind of a ridiculous function, but just more to kind of demonstrate the principle. Okay, so let's go back and let's look at the function that I showed you before. So go ahead and take a second and look at this function, read through it again, make sure you understand it, make sure you know what it's doing. Again, we've got this ES6 arrow syntax. Just to be really clear, what this is just like as if you put inside of here an anonymous function. So it would just say function which takes in a char, and it would just return this line right here. It would just say return reverse chars dot unshift char. So that's all that this fat arrow is doing, if you're not familiar with ES6. So just to walk through this real quick. So we're reversing a string. There's an array of characters. Split the string. For each character in the string, we unshift it into the beginning of this array. To be clear, unshifting puts onto the beginning of an array. It doesn't put onto the end. Pushing puts onto the end. Array puts onto the beginning. If you keep pushing the last elements onto the beginning of an array, you will end up reversing the string. And then you just join that array together, and then you're good. So what should n be for this function? So answer that question for yourself. And so, okay, well, I've already annotated the function for you. So again, make an empty array for each character in the string, unshift them into that array, and join the array together. So let's look at the time complexity of this thing. So if your answer to what n should be was the length of the string, then you got it right. So that's the only real reasonable way to measure how big the input is by how long the string is. So cool. So let's look piece by piece at how long each of these things take. So first we initialize an empty array, this line right here, and that takes O1 time because it's, to make one array, just that line of initializing doesn't take any time dependent on the size of the input, right? Doesn't matter how big the string is. Every time I make that array, it takes the same amount of work or the same amount of time to just allocate an array. So that takes O1 time. So then we split the string into an array of characters, okay? And that's the string.split line. And that must take O(n) time. Okay, now why do I say that must take O(n) time? I say that because, because we're splitting it into an array of characters, in JavaScript, when we split the string, we create a new data structure. And that new data structure is an array that contains a bunch of new objects, which are strings, of length 1, which are each of the characters, right? So I need to initialize n many new strings and put them all into one big array. So initializing all of those n strings must take, O(1) time for each of those strings because they're only one character, right? So that just takes O(1) time because it doesn't depend on the size of the input. But I have to do that, I have to create those one characters n many times. So I contend that string.split must take O(n) time. And it turns out it does. You can measure it yourself if you want. So then I have this for each, right? And for each character, so that means that, whatever happens in this anonymous function right here, this will get called once for each character in that array. So whatever's in here will get called O(n) many times, okay? And then unshifting into this array takes O(n) time as well. Now this one is maybe not intuitive. You might not know why this is. Turns out pushing onto an array is O(1), but unshifting, so pushing on, sort of pushing on the other side of an array, takes O(n) time. Is not O(1). And I'll just explain very briefly why this is. The reason why is that when you do that, you have to copy all of the elements over and sort of push them down by one. And we'll gain a better intuition for this as we start talking about arrays later on in this presentation. But you just have to know that anytime you unshift, you have to copy everything down one cell. Everything sort of has to move down, and you have to move them down one by one. There's no way to batch move things. You just move them down piece by piece by piece by piece. So because of that, this takes O(n) time on average. Now, again, if you're paying close attention, you might notice that, the reverse chars array will start off empty, right? So unshifting onto an empty array, it's got to be pretty fast. And then it'll have one thing in it, and then you unshift onto that, and then it'll have two things in it. So it'll actually have for most of the time, it'll actually be fairly empty. It won't have that many characters in it if the string is size 10,000. But you can do some math to show that the average size of the array, you actually don't have to do much math to show that. You can show that the average size of the array over all those iterations will be 1/2 n. Because on average, if you look into that for each loop at just a random moment, the likelihood is that it'll be somewhere around the middle of having all the characters in it, right? It'll be somewhere around the middle of the iterations. So on average, the size of that array will be 1/2 n. And so you can sort of use a kind of loose law of averages thing to say, the size of the array is going to be on average about half, because about half the things are going to be in there. Therefore, it's going to be about 1/2 n to unshift into the array. So we can go over more of that afterwards if anyone's curious, but basically unshifting takes O(n) time there. And then finally joining everything together. Well, to do that, I have to allocate a new string, right? So I have all these, I have this array of all these characters. I have to, compact them into a new string. And to allocate a new string clearly must take O(n) time because it's a new string that has so and so many characters in it. So that's the intuition there. So the very first part, the O(1) initialized empty array, that clearly is not going to matter because we've got all these O(n) factors everywhere. So we can just ignore that. So let's just not even care about that one. Now, one thing to note is that in this for each loop, right? So even though it's on one line, this is actually a loop that's happening in this for each callback. And inside the for each happens on times, and the code inside the for each loop takes on time to run. Then what that means is that you sort of multiply these ons together, and you get an overall n squared number of operations, or sort of order of magnitude in the number of operations. So basically, the three things that we're going to look at are the on splitting the string into characters, the on joining the characters into a string at the very end, and then this loop, which overall takes on squared time. Okay, and so then if we put that together, we see this function would be on squared plus 2n, which of course reduces to on squared. This algorithm is quadratic. Let's see how badly it sucks. So there's a file which actually let me see if I can get the link. Can someone produce the link? There's a file inside the Git repo. Actually, this is probably a good time for people to, if you've not downloaded the Git repo, go ahead and clone the Git repo into your repository wherever you're working. Because so there are a bunch of files in there, and ideally you'll work through some of those files, run them. There are some benchmarks in there as well. Thank you. Arnaud just posted it into the chat. So there's this file called showslowreverse.js. And I'm going to go ahead and take a look at it here. Oh, whoops. Okay, it looks like, can I switch? Perfect. Okay, so let's look at showslowreverse.js. Okay, so I'm going to walk through this, and I'm going to kind of show you what this is doing and why it makes sense. So Alex Gill quickly asks, hi, what makes an equation quadratic? Quadratic is just a term for n squared. So anytime there's a square in the function, and that's like the highest order or sort of highest rate of growth in a polynomial, we'd say that's quadratic because of the quadratic algorithm and whatever. That's just what it's called. Cool. Okay, so we've got this reverse function, right? This is the one that we were all looking at together. And yes, n cubed would be cubic, exactly. And so I've got this function that just makes it a giant string. So don't worry about what it does. You can just decide how big the string is you want to make it. And so I've got this other thing that's a fast reverse. Okay, so this is a totally different algorithm. For now, let me just comment this and comment this. But if you can, try to follow along and do this on your own machine and kind of prove it for yourself that this stuff does what it says it does. So I want to show you that this reverse right here is quadratic. And so I have this time function that I've written. It's very, very simple. It just sort of benchmarks something. So if you want to follow this code, it just, t equals time, just the time in milliseconds. Then it just calls the function as many times as you ask it to. Otherwise, it just calls it once. And then it just logs the difference in the time now from when the time initially started. So this is just a very, very simple time benchmarking thing that I just wrote. So I'm using this in a lot of files. So if you see this, don't get confused. This is just like a way to time stuff. So, okay, let's go ahead and run this, and let's see how long it takes to fast reverse this huge string. Sorry, not fast reverse. I want to do the slow reverse. I'm sorry. So let's do the slow reverse. And one thing we might also do is just show you, we'll console.log the size of make a huge string length, just to show you how long this string is. Let's see here. Okay, let me make this nice and big. Okay, let's just clear this. Okay, scalability memory, and let's run the show slow reverse. Okay, I have a syntax error. That's always good news. What on earth is happening here? Iterations, syntax error. Is this me? Did I just break things? This is definitely working earlier. Boo, 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 boo. Did anyone else get that syntax error? Oh, whoops. Ruby. There you go. Yeah, too much Ruby. Okay, cool. That's good. All right. So that shows you the size of the string right there, 334611. So it's a really, really long string. And I'm using now my slow reverse function, and it's sitting there reversing it. And this might actually be too slow. to do on camera. It was actually resolving reasonably quickly earlier, but apparently not. So let's make it smaller. So let's make this 8 instead of 9. And let me just clear this actually. Okay. All right, so that's a much smaller string. Okay, cool. So it took 2,418 milliseconds to reverse the string. Okay, and I'm going to now show you the fast reverse. All right, and this algorithm, we're going to look at how fast this algorithm is. Someone I think just asked an algorithm. So we're going to run this fast reverse, and we're going to see how fast this other algorithm is. So that will be the second time that gets printed. The second time was 7 milliseconds, right? So this thing, now if we make this 9, so if we change this number to 9 and make this really big, oh, actually, then it was already for 9. So 9 is like huge, right? So this is like a 300,000 big string. And you can see that the other algorithm tripled. Actually, wait, no, it really didn't, because actually it was the same size. So never mind, that didn't happen. But basically, this algorithm is way, way faster, this fast reverse, than the reverse algorithm that I showed you, because this algorithm is quadratic and this algorithm is linear. And I'm going to show you why it's linear. So let's just kind of develop this intuition here. So first, we established already why split is linear. Split is linear because it has to create this array, and the array will be size, the array will be size n, because it'll have n many characters in it, and each of those will be O1. And when you reverse an array, you can reverse an array in O(n) time. And basically, well, just trust that you can reverse an array in O(n) time. I don't want to necessarily show you how you do that, but if you want to on your own, you can go and write a reverse algorithm and see for yourself that it takes O(n) time. A very simple way to do reverse without doing it in place. So like the simplest version of reverse is you literally just read from right to left and just copy all the elements into a new array, right? If you did that, you would have a new reversed array, but you can actually also reverse an array in place. And so I believe that that's what this reverse actually does, is it reverses it in place. I'm not actually totally sure about that. But yes, you can reverse an array in place very easily because arrays are mutable, whereas strings are not mutable in JavaScript. So in another language where strings are mutable, you could do an even faster reverse without creating any auxiliary data structures. And we're going to talk about that a little bit later when we talk about space complexity. But in JavaScript, because strings are immutable, meaning that you cannot change a string, you can only create a new string that is a different version of the older string. This is sort of the best you can do in one way or another. So each of these steps takes O(n) time. So the whole algorithm is O(n). So I hope that made sense. Any questions about that I can answer for anybody? Or does that all sound good to everyone? Seems like we're all happy. Everyone following along. Can someone give me a sense, like just a quick check-in with the audience? Am I going too fast? Am I going too slow? Should I slow down? Should I spend more time on something? Let me know, because it's kind of hard to really get a feel for my audience when I'm just literally talking at a laptop. Excellent, cool, awesome. All right, then let's move on. So we're going to go through a quick table. This is going to be insanely fast and way too much information. So I believe that this will later get posted to YouTube. So when if this is way too much, which it probably is, you can later go back and read all this again on YouTube and get a big sense to it. Tapan, I'll be adding the slides after the presentation is over. At the moment, they're just on my machine, unfortunately. Okay, so the first time complexity, the very, very, very most fastest time complexity besides O0, which would be literally not doing anything, is constant time. And constant time is expressed as O1. And so we're going to talk about some of the things that take constant time. So any like fixed math, so for example, like 2 plus 2, or I plus plus, or any basic math functions, we'll just basically say that they take O1 time. They're constant. Popping and pushing to an array, those take O1 time as well. It's We'll try to explain if we have time why that is in arrays, but it's just worth noting. Also setting in an array. So accessing an element in an array or setting an element in an array, no matter how big the array is. Even if the array is size 10 million, accessing the element at index 5 or index 5 million is O1 time. Doesn't matter how big the array is, it takes the same amount of time. Property access. So that's like for your JavaScript people. So accessing a property inside of an object. That takes O1 time. Also, if you use a hash map, so ES6, I believe, has native hash maps, that, hash map access takes O1 time. It's actually how objects are instantiated in JavaScript. Conditionals, so, evaluating an if or an else or whatever, that takes O1 time. Like, it takes time to do that, but it doesn't matter how big the input is. And initializing a variable also takes O1 time. So basically anything that just happens once and doesn't care about your input, or particular activities on arrays or hash maps will also be constant time. Cool. So the next time complexity above constant is logarithmic. Okay, and that looks like log n. And the hallmark logarithmic algorithm is binary search. If you're not familiar with binary search, I'd encourage you to go look it up. It's sort of one of the classic algorithms. It's the fastest way to search for anything in a sorted input or any kind of sorted data structure. You can use binary search to find, something in a stack of needles, or a stack of hay. Find a needle in a stack of hay very quickly if you use binary search, because the log of n grows extremely slowly. So, for example, 2 to the 64th, or even, I don't know what it would be. 2 to the 32 is like what is 2 to 32? Can someone post what 2 to 32 is? Can anyone post that into the to the chat bar? So 2 to 32 would be like a huge input size, right? It'd be enormous. You have 2 to 32 elements. But let's see here. So that would be hundreds of thousands, so 4 billion, right? So 4 billion input size. If you have a logarithmic algorithm and your input size is 4 billion, the log base 2 of 4 billion is 32. So basically what that means is that your algorithm would take you 32 iterations to resolve for the input size of 4 billion, which is insane, okay? And if it is literally log base 2, then what that literally means for a logarithm is that if you double the input size, so if you go from 4 billion to 8 billion, then it only costs you one more iteration in your algorithm, which is insane. So there are very few algorithms that are genuinely logarithmic. There are data structures that give you logarithmic access to stuff. So like, popping off a heap or finding something in a binary search tree. Those are logarithmic time, which make them super, super fast for all real world inputs. But logarithms are awesome. And if you have an algorithm that runs in logarithmic time, you're a very happy, guy or gal. Okay, so linear time, this is like the most common, I'd say. Well, not necessarily the most common, maybe it's an exaggeration, but this is sort of most of the standard methods that you'll have on like an array or a string will probably take linear time. So, the most standard examples of linear time stuff are like linear search. If you're iterating over something, so like a for loop over an array or over a string or over, counting from 0 to 20, right? That will take linear time because it's like one thing for each input. So that's linear. So the next up is, so now we're going super linear. The next up is linear rhythmic. And linear rhythmic, it's kind of a fancy word that mostly computer scientists use to sound snobby. For the most part, you can just call this n log n. Everyone kind of knows it as n log n. But you might win brownie points if you pull that out in an interview. And so the most standard n log n algorithms are sorting. So all the standard fast sorts, so merge sort, quick sort, heap sort, all the other variants thereof are n log n. And basically the upper bound, or I'm sorry, the lower bound for comparison-based sorting, basically meaning any sort that like compares elements together, is n log n. That's the best that any sorting algorithm can do if it compares elements. So in JavaScript, if you use .sort, I believe .sort in JavaScript in V8 uses quicksort. Can anyone verify that? You can probably just Google that and ascertain that for sure. But quicksort is usually the most common sorting algorithm, and it's n log n. So quadratic is the next time complexity. This is what we were talking about before. Quadratic because it's shaped like a parabola. The quadratic function, if you remember, what is it, b squared plus or minus something. Yeah. Let's see here. So quadratic, the most common things for quadratic are nested looping. So if you have like, if you're doing a for loop and then inside of it you do another for loop, that's nested looping. So, the outside thing runs n times, the inside thing runs n times, the ends multiply. Kind of the same way that we saw with the reverse algorithm that I showed you, that the kind of crappy one. That was quadratic because we had this outer loop that was doing this for each and this inner thing that took O(n) time. Those multiplied together and we got this n squared. Another example is bubble sort. And bubble sort is this sort of standard crappy sorting algorithm. If you're not familiar with it, it's a good coding exercise to code it up. It is quadratic. It's not very good. It's actually not. There are quadratic sorting algorithms that are used with some frequency. So actually, insertion sort is a pretty commonly used sort, and a lot of standard implementations of quicksort will actually use insertion sort as sort of a subroutine when the input size is small enough, because it actually is faster than recursion. It also has, insertion sort has really good space. But insertion sort is also n squared, but it's much better than bubble sort. And hopefully we'll have some time to explore some of those features as well. I guess maybe not. One question that was asked, actually, I think I missed it. Kate Edmondson asked, how would you measure the efficiency of the reverse method? So we talked about reverse in the last slide. And so it's a nice question. And actually, it's something that we're going to, hopefully you'll develop your intuition about this, because a lot of times you'll call a function in JavaScript or a method on like an array or on a string or something, and you won't really know for sure how long it takes, right? The reality, or the way that I would, encourage you to approach it is think about, you can actually reason about quite a lot of these algorithms about how they must be implemented and how the time complexity must be. So, maybe we'll have some time to go over some of this. I'm not sure how much time we will have for it, but one thing that's really, really just a great skill to have is to be able to make arguments about why this must take at least this amount of time, right? So, for example, I could tell you, I believe that reversing a string must take at least O(n) time, okay? And why do I say that? Well, it must do at least one operation for at least half the elements, or basically for all the elements in the string, because all the elements in the string have to get moved. And if I have to do at least some moving for each element for each character in the string, let's say I'm reversing like a string that's like A, B, C, D, F, G all the way, like there are no repeats in the string, because obviously reversing like a bunch of A's, I could just return it once I know they're all A's. But like I have to at least look at every character in the string and do something for each character in the string. If I have to do that, then it must be at least O(n). And I can sort of make that argument from first principles. So if I can say it's at least O(n), there's no way to do better than O(n) in reversing a string. And I can tell you I know an algorithm for reversing a string in O(n) time, such as, for example, popping off the end and putting everything into a new array, right? That would sort of straightforwardly, or unshifting everything into a new array, that would popping off an array and pushing onto a new array, that would reverse a string using another array, and that takes linear time. And so because I have both of those things, I know the lower bound is O(n), I know an example of O(n), therefore, whatever JavaScript is doing must be O(n), because JavaScript is not stupid, right? You can usually make that argument fairly well. I know JavaScript is a little stupid sometimes, but for the most part, like V8 is a really, really well optimized, hunk of code. So you can assume that if you know an algorithm that can solve the thing in O(n) time, there's almost no way they're not solving it in O(n) time in the actual source code. So this is just kind of like a sort of method of thinking and reasoning about algorithms that's really, really good for figuring out how long something probably takes. All right, let's move on. So cubic time is n cubed, n to the third. So this doesn't show up super often, but basically this is triply nested looping. Matrix multiplication is usually, or the naive form of matrix multiplication will be O(n) cubed. There are actually faster ways to multiply matrices, but the naive version will be O(n) cubed. So then we sort of, this is now not a particular time complexity, but sort of a class of time complexities. Everything underneath polynomial, or sort of cubic all the way to constant, are all polynomial. Okay, if you don't remember what polynomial is from high school algebra, polynomial is basically n to the something plus n to the something plus n to the something smaller, blah blah blah, but nothing bigger than that. It's all n to the somethings. Okay, that's basically a polynomial, and anything that's n to the k, where k is a fixed constant. Okay, like k is not a variable. K is not it's not like n to the m, but it's n to the k, where k is like 40, or k is like 3, or k is 1.5, or even 0.5. These are polynomial algorithms, and computer scientists generally call these efficient. Okay, that's kind of bullshit because obviously n to the 40 is not like no one could ever write a web app that uses an n to the 40 algorithm, or even like a n to the fourth is probably so big that it's just unmanageably big, and no one can really do anything with it. But for computer science, we generally call and anything that's polynomial, quote unquote, efficient. And so if you see that term in computer science, you'll know that means it's polynomial. It's not worse than polynomial. Usually in the real world, we'll generally say anything that's like efficient is usually n log n. Like anything less than quadratic is usually considered to be efficient. Quadratic is like on the verge of being not really scalable in a real world system. And anything above it is like definitely not scalable in a real world system. Like there's just no way that when the numbers get big, you can do like an ON cubed type algorithm, because it just gets way out of hand. Cool. So now above polynomial, we get into like the super crappy time complexity. This is like really bad. If you wrote an algorithm that takes exponential time, unless the problem must be solved in exponential time, you're done messed up, and you're not going to do so good on your interview. Or on building your web app for that matter. So, so examples of things that take exponential time, meaning that they must take at least exponential time, are generating all the subsets of a set. So if you have an array and you want to know all the possible subsets of something, then that would be exponential. And actually solving chess. So by solving, I mean like literally creating a computer that can sort of see all the way through the sort of the decision tree of chess and make perfect decisions and look a million steps ahead or whatever. That computer would take exponential time in the size of the search space of chess. So that's one of the reasons why chess, it's so hard to solve chess, and Go is also an exponential. Any sort of using decision trees to solve a game are generally speaking exponential. And that's one of the reasons why, AlphaGo was such a big deal, because fundamentally Go is like an exponential search space. It's like an exponential game with exponential possible moves, and so to solve it is really, really hard. But they didn't solve chess. We have not solved chess, and we have not solved Go. We can just beat all human players now, presumably with Go at least. But we're still far, far way away from solving either of these games, and chances are we probably never will, unless there's some crazy quantum computing thing that blows everyone's minds. Cool. And so lastly, the last one we're going to look at is factorial. If you don't remember factorial from, again, high school math, factorial of 5 factorial is like 5 times 4 times 3 times 2 times 1. So factorial shows up in a few problems. It's pretty rare. Permutations, if you want all the permutations of an array, that takes factorial time to generate. That's awful. Permutations is horrible. Factorial is totally unmanageable. Basically, it's like past factorial, you get like super exponential, which is like n to the n or n to the m, and then it goes up to. Of course, the worst time complexity is infinity, where you have an infinite loop. So that's literally your program never resolves or just runs out of memory. Cool. So any quick questions on this before we jump into the next exercise? I can answer them now, and then we'll jump into trying to identify the time complexities of some algorithms. Examples of permutations. Actually, so while we're doing, because it's kind of a bit of a detour, not a very important problem. I will add. I'll scrounge up a link while we're working on the tutorials and put it in the chat. So, Kate, if you're curious about permutations, you can read about that there. Alex asks, would recursive functions fall into the factorial category? No. So generally, we're actually going to look at least one recursive function in the algorithms that we're going to try to identify their time complexities. But it depends. So there's some recursive algorithms, like binary search, can be written recursively. That's logarithmic. A lot of recursive algorithms, like reversing a string, you can reverse a string recursively. Reversing a string recursively takes linear time. You can, sorting, merge sorting, quicksort are both recursive algorithms, or they can be recursive, and those are n log n. There are some recursive algorithms that are n squared, and the worst recursive algorithms are generally exponential. And so any recursive algorithm, someone, Yu Yang asked, so recursive function should be at least on squared. No. Yes, Fibonacci without memoization is exponential, but if you memorize it, you can get it to become linear. So basically any really, really bad recursive function, usually problems that are amenable to dynamic programming, the naive recursive solution will usually be exponential. Recursive algorithms can generally spread the gamut. You can do a lot of things recursively, and you can shoot yourself in many ways recursively. But you can also, have really nice recursive algorithms too. Binary search is a good example of that. Cool. Okay. So if there are no other questions, let's jump into it. I'm sorry. We have another thing I was going to show you. So I wanted to show you this real quick graph just to kind of generate your intuition. So this just shows you sort of the rate of growth. These are a little bit bullshit, but it's fine. This is just a graph that I found online. I think it was kind of useful. So this is what an O1 algorithm looks like, basically meaning as the input, this is, the x-axis here is the input, basically the number of elements or the size of the thing you're running through the algorithm. For an O1 algorithm, it doesn't matter how big the input is, it always takes the same amount of time, right? So for example, if my algorithm just like logs something to the screen, it doesn't matter how big the input is if I'm not logging the input. I just like log hello world. And it doesn't matter how big the input is, it always logs hello world, it takes the same amount of time. So logarithmic grows very, very slowly. It almost like levels off. It grows insanely slowly. It's important to note that it does not approach a line. So logarithmic growth is not asymptotic. It doesn't, there's no number that it converges on. It goes to infinity, but it grows really, really, really slowly, which is great. So logarithmic functions are fantastic. This is O square root of n, which is not super common. I don't know why they have it in this diagram. Kind of weird choice, but whatever. On, this is most common. You can see this is literally just a line, right? So it's sort of one-to-one. On squared, this is the parabola that we're talking about, right? So if you remember, the parabola goes up the other side. That would be a parabola, but this here is on squared. And then when you start getting to like bigger and bigger orders of growth, so like on cubed, some bigger polynomial, 2 to the n factorial, whatever, they stop really looking different. They're just like really steeper and steeper curves. So you just draw like a shitload of curves that are just really, really steep. So there's not much point in like drawing much more than that. But just to kind of show you, now one interesting thing here that you might notice, right, is that there's this like critical area, like right here. You can see where like the lines are intersecting each other. Okay, what that means is that if the input is small, this is sort of the way to interpret this. If the input is small, it's not actually true that a quote unquote more efficient algorithm will be faster. Right? Because you can have, for example, an algorithm that's like, on plus 1,000, and then an algorithm that's like, 1/8 n squared plus 10, right? And if the input is small, then the 1/8 n squared is going to be faster than the 1,000 n, right? But eventually, no matter how big those constants are, there will be some point where it escapes this area, where this area is left, and like the lines just diverge. They never get close to each other again. They all sort of grow infinitely apart. And on squared is just going to always and forever take more time than on. And then log n is always and forever going to take less time than the on. So inside this area, so basically, kind of the way to interpret this is that this is what I mean when I say that big O is not about speed necessarily. Okay, big O does not necessarily tell you. The y-axis is time, like the amount of time that it takes given a certain input size. So big O does not actually tell you which algorithm will be faster for a fixed input. Okay, so it might be that, like, for example, I talked about an example earlier of insertion sort. Insertion sort is n squared. Quicksort is n log n, right? That is less than n squared. But for small inputs, insertion sort is actually a lot faster than quicksort. And most standard implementations of quicksort will actually take advantage of that. So it's not true that for all inputs you want to choose sort of the more quote unquote efficient algorithm. And a lot of times actually on embedded systems or on like low level programming, like if you're programming like drivers or something where memory is very constrained, performance and efficiency really, really, really matters. And that inputs are going to be of fixed sizes. In those cases, actually, you don't want to be thinking about big O. Big O is the wrong frame of mind to be programming in. The right frame of mind to be programming in is benchmarking and like actual time-based performance, right? But as computer scientists, and especially as people, building, if you're building web apps, or you're doing web development in JavaScript, then you want to be thinking about scalability. And scalability is all about big O. It's all about when we leave this sort of central area where the algorithms intersect with each other, then they never meet again. And when they never meet again, that's sort of the area of like computer science and asymptotic analysis. So I think it's nice to look at this and kind of get an intuition for what it all means when we're actually looking at algorithms and real world applications. Cool. So what we're going to do now is we're going to take a look at some time complexities. So there's a file called, let me close this and take a look. There's a file called timecomplexity.js. So if someone could link to it in the repo, if you want to find it exactly. But it should be in the repo. If you clone the repo, you should be able to find it. You can also just go copy and paste it from GitHub into a file if you want. And all I want you to do is just mark in a comment each algorithm and its big O runtime. So just right below here, just say I think this takes O of n to the third or whatever. That's not say that. Cool. So what I'm going to do now, just so that we have some division in the videos, we're going to take a little bit of time, maybe 10, 15 minutes, and I'm going to switch sessions to the next session. So it's going to be a little bit weird, but we're going to all move to another, let me see how I do this. We're going to all move to another window, and we're going to go.
How come I can see him though?
Yeah, we're back to number 1.
Wait,
Oh.
you're in, no, you're in session
Okay.
1.
Is this working again?
We can see you, but we're back in session 1.
Okay. Let's just screw the session thing because I have no idea why it wouldn't let me broadcast from the second session. Oh, I think I know.